Okay, so again, if anyone doesn't have any logic called up, please do so now. So today's class, we're going to be hitting on a number of particulars. The two major topics that I'd like to cover are a very different sorts. One of them concerns sort of a purpose, goal, sometimes even a philosophy of modeling that will be a little bit distinctive, and I wanted to highlight to you what I call stylized modeling. Modeling for insight is another term for it sometimes, as compared to sort of for empirical, to directly map to empirical observations. And second of all, we're going to be talking about spatial context, capturing spatial context within our models, and particularly in 2D landscapes. So when I first introduced motivations for modeling, I gave this example of, or this analogy that models are thinking prostheses. What's a prosthesis? Anyone tell me? We talk about a prosthesis, a prosthetic arm. What are we talking about? I'm sorry? Okay, replacement is part of it, okay. Often it is a substitute, but a prosthesis might be something like a crutch also, or a cane. So what do all those have in common? A prosthetic arm, a cane, a crutch. Well, they all have in common the fact that basically they're designed to help make up for limitations, make up for our shortcomings, help provide our ability to function despite certain limitations. So if we're missing, if we've had an amputation, we use a prosthetic arm to make up for that. If we're really unsteady in old age, we might use a cane, right? So in all these cases, we're seeking to have something that will complement our limitations. And that's what models do, I argued. I argued that models help us complement our very limited ability to think logically through the implications of assumptions about how things might work. We're not very good at totaling things up in our heads, a theory, and playing it out directly. And while we can try to sit back and do Goduncan experiments and imagine something playing out according to certain rules, it's very easy for us to make mistakes. By contrast, computers are extremely good at this sort of activity. We can describe to them certain rules and they can tell us, they can play out for us the logical consequences here. So I argued that, models here sort of serve to help us think through the logical consequences of our assumptions much more deeply than we could. And because of that, they can help us learn more quickly. They can help us learn more quickly by helping to explain observations better, helping us to identify inconsistencies between what we think might be happening and what might actually be happening out there in the world. Now, stylized models play in this role, but they're particularly aimed at helping us sort of towards high-level insight, helping us think through some quite simple assumptions. What are the implications for the broader system? How a simple set of mechanisms or mechanics can yield unexpected results or explain some patterns that might otherwise be puzzling. So here, we're not seeking to recreate a particular circumstance. We're not seeking to recreate something about Saskatoon and its road network, something about a particular company and its competitors, something about a particular pathogen that's spread in the population. We're instead seeking to kind of understand some general principles about how certain assumptions might yield natural consequences in a way that's deeper than we could think through directly. So they're abstracting away from lots of details about particular real-world situations and focusing on a few essentials. So they're a little bit like a caricature of a model. You folks have all seen them, right? Caricatures, maybe political caricatures. They show prime ministers, for example, with giant chins or big noses that stick out. They show them with exaggerated features, perhaps the ears or what have you. And they're not meant to be an exact depiction of a person, but they're to draw out some essential truth about the situation, some essential feature that will help you recognize a person, help you recognize a certain character or what have you. And so it is with these models. They help point us to sort of certain core realizations that we wouldn't have had otherwise. So we're going to be talking in this context of stylized models about spatial embedding, and we're going to do a brief review of a type of spatial embedding we've been using thus far, to wit, continuous space. And then we're going to be taking a look at a glimpse of discrete space and discrete time. And if we're lucky, we may get to finish a given example of that with mobility as well, with mobility in discrete space. But first, we're going to be taking a look more generally at this topic of agents spatially embedded and how we capture it within these models. Okay. So what we're going to be taking a look at is this issue of sort of placing agents within space. And there's some good reasons that we might want to do that. Can anyone in the audience suggest why might we need space to be represented in our models? After all, thus far, we may have had networks, we've had populations, but we haven't had space. Why might space be important to represent? Give me a couple reasons. Okay, good. So we maybe we want to reproduce a geographical distribution of things. So we want to reproduce how people are scattered around space because, and it's typically because it is important for something. That thing could be so that we can have a certain amount of convincing power that our model has captured some important features. But often it's because we want to capture certain dynamics. The fact that people cluster in a certain way might lead to certain risks for them. The fact that it might lead to traffic jams at certain places, for example. It might help us understand why we see certain patterns over time, and perhaps the explanation for that might be hypothesized to lie in sort of the geographically mediated interaction. In other words, the fact that two people near each other tend to interact more may explain the patterns that we see. So spatially embedding agents can be really important for capturing certain underlying dynamics. And that's a very good reason for capturing. It can also be important for explaining, for example, different outcomes amongst the different group of people. Perhaps people in different regions of space are affected less or more by a certain investment or by a certain policy. Finally, as part of this, it can support GIS integration. And we may go through that in a coming lecture. So basically in AnyLogic, there's three supported mechanisms. And not surprisingly, these correspond to the three most common ways of capturing space in models in general. Number one, continuous embedding. Number two, discrete cells. And number three, GIS. Okay. GIS stands for, anyone know? Geographic Information Systems. So these are information systems that make use of information about the world that is geographically based. What is where, in short? What is located where in the world? Or how close are different things? What's the nature of the terrain in different places? Where are the lakes? Where are the roads? Where are the rivers? Where are the bridges, etc.? Now, each of these has some discrete features to it. Continuous embedding has certain basic assumptions associated with it. The idea here in AnyLogic is that agents who are embedded in a physical landscape, a continuous landscape, they're basically assumed to be small enough that they don't interfere with each other directly. There's no enforced requirement that they can't cross paths, for example. They can't pass by each other. And we've seen continuous space by distributing agents around the space. Remember when we did that? We plopped agents around space. We said random layout, or we said uniform between 0 and 500. Okay, so this is one type of environment which agents can be placed. We're going to start there. But we're then going to go to a separate situation where we have agents described in a discrete way. And this goes way back in the history of modeling, back to von Neumann. Anyone heard von Neumann's name before? Anyone know anything about him or anything else he's responsible for? Maybe in 215? No? Doesn't ring a bell? Professor Eager didn't talk with you about John von Neumann and his contributions? So the notion of a von Neumann machine. John von Neumann, amazing guy. He was a physicist. He was a mathematician. He was an early computer scientist. And he came up with the idea that central to most computers operating these days, that a computer would consist of a CPU, a central processing unit, one or more, and it would include memory, and the CPU would go through and write and read things from memory. Its instructions would be stored in the memory, and it would be governing the contents of memory, and then there's various sorts of I/O, input and output, that bring data in and out. This is a von Neumann computer. And von Neumann contributed in a central way to developing the theory of how today's computers work. So this is a von Neumann computer, von Neumann model of a computer, okay? It's a model of a computer that's the dominant one. So John von Neumann, in one of his areas of computation, came up with computation that was very different from this. It consisted of what he called automata, and what are now called cellular automata. And here you divide the space up into rows and columns. So you have a certain number of rows and a certain number of columns. These are discrete things. Each row and column contributes to a grid, and within each grid cell, you can either have 1 or 0 agents. 1 agent, 0 agents. And it turns out that anything you can do with the von Neumann computer in this form, you could do with the cellular automata. You can define, and it's quite straightforward to define a cellular automata. In fact, we'll be discussing one of them within the context of these grid cells. So we here have the columns, and we have the rows here, and we'll have particular cells occupied. And there will be rules as to how cells evolve over time. They may evolve based on the cells around them. They'll evolve in some way. Anyone seen a situation like this or a game like this before? Yes. You got it. Conway's Game of Life. And it's associated with the mathematician Stephen Conway, I can't remember his first name anyway, from Britain, who first came up with these rules. And this is a cellular automaton. Cellular automaton. And von Neumann came up with this idea, too. And he realized that anything you could compute this way, you could compute this other way. It's universal model of computation. Anything a Turing machine can compute could be computed with either of these. They're Turing universal. Does that term mean anything to people? How many people have heard that before? Turing universal. Okay? How about Turing machine? Okay? Yeah, it's a Turing, not Touring. It's not a machine that travels around and takes tours. It's a machine that was first established by Alan Turing, the most famous computer scientist of all. So anything that can be computed by Turing machine can be computed by certain types of cellular automaton and von Neumann computers. And von Neumann came up with both of these. So he contributed to both types of computation. So it goes way back in the theory of computing, and that's what I call a discrete model. And in AnyLogic, each of these cells can hold one agent or zero agents. Indeed, there are other agent-based platforms where that's the dominant model of sort of representing things. A final component is GIS embedding, where we actually link in information about agents to their spatial landscape. Okay, if we deal with that, it'll be in a separate lecture. Okay, so in AnyLogic, in main, there's this area of it called the environment, and it sets the parameters for the 2D landscape, whether it's continuous or discrete, what its width and breadth is, if it's discrete, how many rows and columns it has, and then if it's discrete as well, the nature of the neighborhoods, whether it's the 4 cardinal directions, north, south, east, or west, or whether it's in all 8 directions, northeast, southeast, northwest, southwest. Okay, so let's go to AnyLogic briefly, and let's take a look at this environment. Okay. So here we are in AnyLogic. Let's go call up a new model, and let's call it simple mouse-driven mobility. How do you like that? And it'll be CMPT for me, 394, fall 2015. And let's make the model time units. Sure, we'll make them seconds. That's fine. We'll leave it at that. Okay, you ready? Okay, let's go create it. Okay, terrific. Okay, so I am going to go create here in the palette. I'll go close other things here so they don't distract us. Close others. There we go. Great. I would like to go add in an agent, okay? We'll do new model, and we will say, what do we call this? It could be called any sort of things. We could just call it droid. Let's call it a droid, okay? It's going to be a droid that's going to move around in some stylized fashions. Okay, great. So here we've gone and, hey, oh my gosh, I created a new model called droid. Don't do that. That wasn't what I meant to do. Sorry, folks. I zoned out for a bit. You're probably wondering, what the hell is he? Okay, I'm going to call this droid. Okay, there we go. We have a droid. Okay, we've added a droid. And let's go give it a representation, right? So that we can see it. Well, you folks might want to use different representations. These are some pictures, but we could go and add more. I think for simplicity, I'm just going to add a simple thing from presentation. Here we go, and I'll add in an oval. I know it'll bore you folks, but that's not the point of this. There we go. Okay, so we've added a droid representation, and now what I'd like to do is I'd like to go to main, okay, and I'd like to go down, and you will notice further down in main, there's a space and network area. This is kind of the environment area where we're going to specify the environment. So I'm going to say, let's make it a continuous environment, okay? We're going to leave it with these dimensions, 500 width, 500 height, Continuous. Great. Okay. Now, in main, I would like you to go add in a population of droids. I think all of you know how to do that. I'm going to drag it in from there, and it's going to be called the population, yeah. And we're going to set it to be a population of 100. Okay? Great. We're going to just leave that to be 100. It's going to be a population of agents, right? Okay, excellent. Okay, now we're going to do something a little bit different now in order to, okay, actually, before we do this, let us go and let's give these droids some behavior. First of all, we want to scatter them around the space. How are we going to do that? How are we going to scatter them? We've done it several times before. We've done it two different ways. Does anyone remember the way? Okay, good. Yeah, so set the location of the population, and we're going to specify the agent as starting initially at the specified point, and we will scatter them around as being between 0 and 500. Okay, great. Hey, come on, get back here. Great. Here we go. 0 and 500 on X and Y. Good. Okay, I don't know why this is truculent. Okay, 0 to 500, 0 to 500. Okay? Great. Now, let's run the model and make sure we're hunky-dory before the next stage here, because it's going to get more interesting shortly. So run the model, build it, run it, and you should see something like that. Everyone see that? Okay, Alan's in the back, and we'll soon be on the prowl for people who need help. Okay, we're in good shape. Let us now, ladies and gentlemen, go to droid. Now, here's the challenge for you. I want the droid to engage in random walk, a random walk. I want it to move around in going random directions. It will go for a certain amount of time. It'll pick a distance to go, pick a new location. It will go there, and when it arrives, it'll pick a new direction to go to and go there. How would I implement that? Anyone? Given the building blocks that we have here, how could I implement that? How would I implement it? Good, state chart. I like it. So let us go, and we could go to the agent, or we could go to the state chart. Let's drag this in, and we call it mobility state chart, right? Good. Okay. And I want to drag in a state here that will be called in motion. Okay? And in this case, within the state chart, there's actually going to be only a single state, which may seem odd, but it'll be what we need. Okay. So, we're going to now put in a transition that's going to go from this state back to itself. And what sort of transition will this be? Anyone? Remember our choices for transitions. You've seen them before. What would this be? What do you think? It'll be an agent arrival transition, when they arrive at their destination. What do you think was going to happen when they arrive at their destination? They're going to change direction. They're going to go a different way. Okay. So this is good. So, ladies and gentlemen, go to the in motion state here, and we're going to set them off in a certain direction, okay? We're going to set them off in a direction that puts them near their current location, but has a disturbance to it, or as we say, a perturbation to it, okay? We're going to move them to someplace nearby, but with a certain displacement. Okay, so ladies and gentlemen, the entry action to this, regardless of whether they're going out and coming back in, or whether at arrival, or if they come in here, we're going to do this dot move to, and we're going to move them to a certain place, okay? To what place will we move them? Well, first, with move to, we need to specify the X and the Y locations. You could see move to as several different forms, but one way is to specify the X and the Y, okay? So let's go do this. Move to, for the X location, we're going to draw a value that's from a normal distribution with a standard deviation of 20 and a mean of their current value, this dot get X, okay? There you go. And we're going to do something very similar for the Y. We're just going to do this dot get Y, and we're going to close that, okay? So for those who can't see from the back, I will call up a notepad so you could see this, okay? Okay, accessories A. Oh, man, I didn't want that. I don't know what that is. It's a note. I wanted a note, not a notepad. Hey, not that sort of notepad. Boom. Yes, I want to delete it. Okay, here we go. This is what I just did, right? Who can interpret what that does? Speak to the dignity of your profession. What does that do? Mm-hmm. Yep. Okay. So basically, yes. Okay, this normal is a draw from a normal distribution. It samples from a normal distribution. In other words, you have a normal distribution that's centered at your current X position, right? It looks something like this. Here's your current X position as indicated through getX, and that returns my current position. And I'm drawing from a normal distribution with a standard deviation here, a sigma, equal to 20. So I'm drawing a value from this distribution. Does that make sense? And I'm using that for my X. I'm saying move to, that is my X, and this is my Y location, to which I'm going to go, is drawn from a normal distribution around my current Y location. Are we okay with that? Okay, great. So this is what we're going to do. Now let's run this thing. What do you think will happen? What will you see? What specter will lie before you? Can anyone describe it? What do you think you'll see? So what's going on there? Yeah, okay, good. So they're moving around in what's called Brownian motion. Have you heard that term before? Brownian motion? It's sort of what molecules are believed to do. They sort of jiggle around. You also see it in financial sector and for financial instruments, like with the stock market. Stocks locally may exhibit sort of Brownian motion. Okay, so that's great. So that's a good start. We have this. That's pretty nifty. Suppose we were to, I would challenge you folks. Perhaps we should allow agents to have some influence of other agents. So if there's an agent nearby, they move towards that agent, perhaps, or move away from it. That would be a pretty interesting possibility. So we could have in here, for example, a branch with a certain probability they move towards the nearest agent, right? What do you think would happen if we did that? Let's what the heck? Let's do that. these class sessions are supposed to be interactive. So what do you think would happen if we put in a branch here and had them move with a certain probability? They go to a randomly chosen location. Another probability they go towards the nearest agent. What do you think would happen? Would you see that same behavior basically? Okay, I like what you're hearing, what I'm hearing. Would they just kind of float away from each other in that way? Probably not. Okay, so ladies and gentlemen, rather than doing this in motion on the entry action to there automatically going to a perturbed location, let's instead do it. How would I do this? Well, first of all, I need to move this up to the entry, up to here. So when they first come in, go this way. And then I'm going to have, by default, they will undertake this random motion, but with a certain probability, they will undertake, so with random true with a certain probability, right? Let's say 0.1, they will undertake motion towards a neighbor. Okay? There we go. And how would I undertake movement towards a neighbor? Well, this dot move to, and if you look at the options for move to, you notice that you can go directly to another agent. Okay? Great. Okay, this dot move to, and I could say this dot, and my memory is get nearest agent. I can get nearest agent here as an option. Nearest point on segment, nearest connections, get network connection. I think it's get nearest agent. This will be probably our ticket. And let's just use that. Okay, get nearest agent. And we are going to give it as a list of agents main dot population. So it can choose any of them from the population that I'm closest to. Okay? So here, if I go this route here, and I'll make this a little bit bigger and more obvious. So basically, when I arrive at my destination, I have two possibilities. I can either go to the nearest agent, or with 90% probability right now, I will continue to just sort of engage in Brownian motion. Another possibility is we could see if the agent is close enough to us within a certain threshold we could go. There's all sorts of alternatives, and I'd encourage you to try to come up with a fun alternative. In fact, if you do that, I will include that in as a contribution towards the next pop quiz. Here we see movement. Is this behavior different or same than before? Anyone? It's a little different. We have agents kind of clumping together. They're not just kind of going off. Let's what the heck? Let's go up to main, and let's put into main here. Let's go put in a parameter, and we will call this probability of random movement. Right now, that probability is what? 0.9, right? Okay. And we will go down here and now, having put that in main, this random true will be random true of what? So if I had the probability of random movement, what should this probability be? After all, this 1 minus that. That's right. Main dot probability of random movement. Okay. Fun. Okay. so ladies and gentlemen, let's do one more thing. I have the goal of teaching you several things during this lecture. Let's go back. So what did I do? I added this thing. I set its default value to be 0.9. I went down to this here, and I set this to be random true 1 minus main dot probability of random movement to go this direction. Okay? Are we okay with that? Okay, now go back up to main. And ladies and gentlemen, I would like you to go and add in to the model from this controls area here, controls, I would like you to add in a slider here. Okay? And this slider will be linked to, and pick it, the probability of random movement. And it's going to go between what? What are the two values? Well, it's a probability, so between 0 and 1, right? Great. And we should probably put a label to add it. So you do add labels here to make it clear, and we will call this slider probability of random movement. Okay, who needs help? Okay, and probably it makes sense in the presentations area to go drag some text in and say, you know, in the text area, this would be text slider label will be the name of it, and the text will say probability of random movement, that probability that an agent moves randomly. Okay? Great. Okay, ladies and gentlemen. Yes? Sure. In the droid, here we go. It's for this transition here. Yeah. And the condition is random true. It's like this, Alan. Remember, this parameter should be in main, right? Are you okay with that? Okay. Okay. This default is this one here. It's just the thing we had before, Alan. The default was just this thing. This thing is just what we had before. Okay. Okay. Now I'm getting a. Okay, slider cannot be resolved. Oh, we called it. Okay. It's this guy's unhappy. It should be called slider probability. I added these labels in, and they refer to the old one. I should have refactored it. Probability of random movement. These three things here. Probability of random movement. Okay, there we go. So, what do you think, ladies and gentlemen? As we increase the slider, how should this vary? Who needs help? Who would like me to wait a bit? Okay, wait a little bit. What would you like me to show? The slider is here. The slider, I said, link to this parameter, and I said it had a minimum value of 0 and a maximum value of 1. Okay. Who else would like me to show something? Okay. What would you like me to show? This is 0.9 initially. It's a double. It's 0.9 because that's kind of what we were assuming, that with 90% probability. Great things. Who else would like to ask a question? Who else would like me to show something in the model? Do you want me to show the droid? Here it is. Here's the default, and here's going to the nearest agent. Okay? Okay? Okay, who would like me to show something? This guy here is still on a timeout, and you have this. This is the default transition. sorry, this is the condition here, and this is the default. That's why it's a slide. It's a dotted line. And now, ladies and gentlemen, when you come in, you also need this because you need to get going towards something. So you also need this when you come in. Okay? Are people okay with that? Okay. So, ladies and gentlemen, who would like me to show something else? Are we ready to run it? Ready or not?
Sorry, can you show how to get the value
slider? How to get the value from the slider? Yeah. The value is automatically linked to this. So I said in the slider, I just said link it to this, and that means if we adjust the slider, we'll automatically adjust the parameter. See, it says link to here for the slider. Do you see that?
Sorry, I meant for like
this thing. This thing here? Yeah. This thing, I just referred to the name of the slider, .getMin.
Oh, okay.
Name of the slider, .getValue. Name of the slider, .getMax. See that? Yeah. Okay. You ready to roll? Are we ready to go? Okay. I'll take that as a yes. Okay. Here we go. Okay. How do you think this movement will increase? If I move it to 1. Oh, wait a minute. Yes. Okay. If I move it to 1, now we have these sort of jiggling apart. How if I move it down to something like 0.01 rather? What are we seeing now? Characterize the nature of the interactions. What's going on? They're forming small groups is right. Okay. How if I move it? I'm going to move it to 0. What's going on here? Think through. What's going on? Why do we see this? You got a bunch of them on top of each other. They just move to the nearest agent and they stay on top of it. Boom. Okay. Here we are. Okay. How about midway? What do you think is going to happen here? Well, it'll be sort of like a combination of both of them. Okay. Let's try it down again. Okay. They're moving closer together. Okay. So here we have a sort of little system. Without building this, I'm not sure how many people could have guessed what this qualitative movement would have looked like. Would you have guessed that way down here you get these things kind of just jiggling next to each other? Here, up here, Brownian motion, you might have guessed it. Now it's getting more entropic. Look at that. Take a look at that compared to like this. This is much more muted and much more clustered in its implications. Do you see that? So here we have kind of a spectrum of values associated with the model. And in fact, if we had started off from the very, okay, I don't want to do that. That's adverse. Okay, let's try this again. And now if we moved it down all the way here from the very get-go, they probably wouldn't have spread out nearly as much. Just kind of shifting around and staying with each other quite a lot. The more they're just kind of clustering in here. This is getting more entropic. Up here, they're going around, they're passing each other like ships in the night. So that helped us think through the natural implications of our understanding, better than we could have done in our head for what the consequences are of this little model. I've also taught you how to set up this slider, link it in, and I've taught you how you can get these guys to go to certain locations. But our job isn't over yet. Let's do one more thing. And my purpose here is to teach you another skill. Go to main, and ladies and gentlemen, who would like me to answer any question about that, though, before we go on? Anyone want me to show anything? Anyone want me to? Okay, what would you like me to show, Garrett?
Just go through each element
Sure. Okay, so I'm wondering, do you have a code associated with this entry point? That is what you want, because you got to set it in motion for it to arrive. It ain't going to arrive anywhere unless you set it in motion. So in the entry to the state, you need this guy here. Okay. Well, but Alan, it also needs to be here. Otherwise, it won't. So here it needs to arrive. It needs to get started, and then here, this is just sort of if it chooses random movement, it does this. Okay. Who else wants me to show anything? Okay. Okay. Here, let's make this interactive, a little bit more interactive. So go to main. Here we go. Let's go up to main. And let's go up to here. We're going to put a rectangle in main. How did I do that? I went to presentation. I dragged a rectangle up to main. And I'm going to click on this rectangle. And I'm going to do order send to back. So it's behind everything. You okay with that? So I just put in this rectangle. I'm actually going to set the rectangle to be of width 500 and height 500 as well, as set by its position and size. So it's the size of the original space, 500 by 500. And ladies and gentlemen, this rectangle will now appear behind the agents, right? Should we run it? Make sure, okay, there's a rectangle behind there. I mean, you may not even visually really see it, but here's a rectangle there. Great. Okay, now, does everyone have the rectangle? Does everyone send it to the back? Okay, we're going to do one more thing that's going to teach you an important lesson. So, ladies and gentlemen, what I'd like you to do now is to do the following, okay? Okay, now we can either do this in a way that will stretch the horizons of those in the room, or we can do it in a way that will let you fall back into complacency with your established habits. Which would you like? Okay, we're going to do the first of them. Thank you very much. Okay, so ladies and gentlemen, I would like you to go to the rectangle, and I would like you to go down to the advanced area. Okay? Okay, now it's going to get fun. Okay, go down to the advanced area. On the rectangle that we sent to back, remember to send it to the back, right? By right-clicking on it. So in the rectangle, scroll down in its property pages to on-click. And now, ladies and gentlemen, watch this. Okay? Okay. Population dot for each D as in droid. So for each, does anyone remember how that worked from before? What do we give for each? We give it a function, a lambda expression. Okay. So this function will take in a droid, and what will it do? It'll say droid dot move to, and we're going to move it to click X and click Y. There we are. This is what I'm putting in that box for this is going in the on click. Where does this click X, click Y came from? It came from what's suggested here. If you mouse over to this little light bulb, it says use click X, click Y, shape relative coordinates. So what is this doing, ladies and gentlemen? What does this accomplish? Moving all the droids to my click location. Are you ready? Are you ready, ladies and gentlemen, to command a fleet of droids? Is that a yes? Okay, thank you. Thank you. Okay, we want to command the fleet of droids, okay? Okay, so ladies and gentlemen, let us now run this model, and boom. Okay, what's going on? What's going on here? What's going on? Good. Every droid in the population moves to where it clicked, and then it starts expanding again, right? Okay, now let's suppose we actually have them be highly philic, so they like to stay with each other. What do you think's how's that gonna change things? So suppose they're totally entropic, all the way at the end. They just engage in random movement. They don't pay attention to where each other is. They converge, and then what happens? They immediately start diverging, right? Okay. Suppose we make them all the way down to 0.05. Suppose we drag them together. How do you think it's different? Well, they stay much more clustered, right? They like being around each other, so they don't tend to wander nearly as much. There's kind of this attractive force which keeps them in a given area. If we have them be entirely preferential, well, okay, then okay, that's interesting. Okay, I wouldn't have, oh, look at that. They're moving, yes.
I think they pick themselves as the target they move to in that case. I think so. That's my theory.
You think they move to themselves? I don't know. Get nearest agent shouldn't move, it shouldn't return itself. Okay, it's an interesting question. Why are they not moving to, okay, so let's go debug this. Okay, let's go figure out what's going on there. Okay, first of all, how would we debug this, ladies and gentlemen? How do we debug this? How would we figure out what's going on there? Why they're not moving at all? Well, make a separate copy of this model, call it debug at the end. Okay, great. Now we have free license to investigate with abandon. Okay, so I just saved it. I'm going to main. I'm going to set the population to be 2 agents. I want to study it in a very simple way. I'm going to have 2 agents together. Okay? You ready for that? First of all, let's run it with 2 agents. Let's see what's going on. We don't actually need to change the whole model to do that. We could have set up a different experiment. Okay, so here they are coming together, and they zip around. Okay, now let's set them way down at this side. Okay. Okay. Does anyone see what's going on there? Watch this. Anyone see what's going on? Let's try this again. Let's start over. Watch this. I'm going to move this all the way down to here. What's going on? They're going to their last location. That's right. Remember. That's right. So so I say, okay, I want to seek out a friend. Where's the nearest friend? He's over there. Where's the nearest person? He's over there. I'm going to go there. And meanwhile, as I'm going along, what's he doing? He's going to me, right? We pass each other completely blindly, right? And so we're oscillating back and forth. And sometimes there's a random movement because it's not totally zero here. They're sort of zipping around. They're getting kind of closer to each other. Okay. So our model didn't quite cut it. We didn't quite capture what we were hoping to, which is kind of go to the nearest friend where they are right now. How would we capture that in this model? Well, okay, but have we debugged this issue? So let's go turn it down to 0 here. Look at this. So what's going on here? It's 0. So they're just going to the nearest one. Okay. Bingo. They're on top of each other. They are clearly going to a different agent. They're not going to themselves here. They're going to a different agent, but eventually they get on top of the other agent, and then they just sit there in bliss, just atop this other agent. Okay, so ladies and gentlemen, suppose we wanted them to go to the nearest agent on an ongoing basis to actually track where that agent is. What do they need to do? How would we capture that? So they should be tracking the agent to which they're going. How do we do that? I like it. But the key thing is right now, we go to the agent. We pick the agent to go to, right? And then what happens? When's the next time we check anything? When's the next time? When we get there, which is where that person was 5 minutes ago or something, right? So we need to actually check more frequently, right? We need to get in this state of like seeking out our friend, right? So how do we do that? How do we, I even use the word, how do we do that? How do we get so that we're seeking out our friend and we keep on updating? What's the easiest way to do that? We could add another what? We could add another state where we're basically seeking out a friend, and then we have a chance of moving back to this sort of entropic state. So now we're kind of redefining our diagram to capture the behavior. We didn't understand, ladies and gentlemen, the implications of what we put into place. We didn't look ahead enough in our minds as to what behavior would be elicited. We thought it would exhibit this behavior of going to your friend, but it led to this behavior of friends just passing each other, seeking each other out and just passing in the night because they weren't updating their things. So that's not quite what we wanted. We didn't previously think it through. So now let's suppose we have a friend-seeking state, right? Great. So now this transition here, where we're moving to the friend, where should that go to? To where should that go? Whither should that go? To the friend-seeking state. That's right. And in the friend-seeking state, we will have a certain, what will we need to do in the friend-seeking state in order to successfully seek them out instead of passing them like a ship in the night? What we need to do here? Ladies and gentlemen, we will need to periodically check up on them, right? Okay, so this one here, I would argue that instead of doing it like this, where the action is here, where could I put this action? In this entry action for the friend-seeking state. And so when they come in via this transition, they'll seek out this friend. And then periodically, say with a rate, every 1 per second, they will sort of check, then update, and go to the nearest friend. Okay? Okay, this is going to be fun. Okay, so what's the implications if we just do it this way? What's going to happen? Suppose we put this into place. What's the implication of it, ladies and gentlemen? What will happen if I run this? What's the logical implications of this? I'll just go to the nearest friend and hang out there, right? Okay, so here's our two agents. Okay, there we go. Okay, wonderful. Here we go. By the way, I should be careful. We should be making sure that this is running with a random seed, so every time is different. I just went to the simulation, went down to random seed. Okay, that's great. So, ladies and gentlemen, we have here this kind of movement, but we still need sort of some entropic movement. So maybe we'll rename this in motion state. We'll call this, Brownian motion state. Okay, and this is where they're basically moving around, jiggling around in this way. And what we need is a transition between them. So with a certain probability, they will engage in that Brownian motion state. They'll kind of forget about seeking the friend, and they'll engage in this with a certain probability. Maybe what we'll do, just to keep this clean, is that we'll make it okay, so I was thinking, okay, that would occur every time you've arrived at the friend before. Now we're going to go between these states with an average time. Let's set it to be an average time here of every 10 seconds they'll go back to the state on average. So I could make it 1 divided by 10, right? So they'll go here on average within 10 seconds. Okay, let's give that a try, and then we'll come back and fix that up a little bit more conceptually. Okay, so here we have these things in these two states, and this is not exhibiting movement. It's not exhibiting Brownian motion. So why would that be? Well, you'll notice that here they transition. It's not clear which state they're in. Let's go add a bit of debugging. Let's go set a variable to be color here, color, and we'll make that variable of type other, and it will be type color here. So type listed here other, and it'll be type color. And in this state, we will set them to be color to be red. Otherwise, we will set color to be green. Okay. Otherwise, color equals green. Great. So their state will be obvious, and the oval needs to be that color. Right? So if we go up, so I created a variable other of type other. It is the type of it is color. I then set color to be red here, and I set color to be green in this state, and then up here in oval I made it fill color to debug what's going on. I'm trying to teach you some debugging skills. Number one, simplify it so it's only a few agents. Number two, go and take a look at what's going on. Okay, this one's wandering. Okay, now those two are there, and now they're perpetually there. Why are they perpetually there? Okay, now, okay. Why aren't they moving? Why aren't they moving? Here's color, here's person one, here's person two. Person two, you'll notice, is in the Brownian motion state. Person one is in the friend-seeking state. Why is it that this guy isn't moving? Anyone? Debugging skills. Why is it he's not moving?
We don't have an action in the transition from friend-seeking to Brownian motion.
Right, exactly. So here, ladies and gentlemen, we didn't set him in motion. So he could have been at rest when he transitioned, and in which case he would have never have arrived, and therefore this transition will never take place. So what we need is an action associated with this, and my suggestion, ladies and gentlemen, would be to go back, now that we've simplified, now that we've sort of regularized this, to go back to the situation, now that we have two states, where we have this move to within this state here, okay? So we have move to here and instead of in here, okay? So, and instead of in here, we have move to just in the entry action here. So we're moving, as soon as we come in here, no matter which way, we're jiggling around. Okay. So all I did is I consolidated it. Instead of having this action to jiggle around in both these transitions, I put it in the entry action to this state. So I would like to run this now. And now we will see this sort of behavior. And then at some point, they will start wandering around. Okay. Now we're seeing a somewhat different behavior. One of them's in a wandering mood, and the other's in a friend-seeking mood. And the person seeking out the friend goes after the wanderer. All right? So there's the wanderer going around. The friend seeks him out. Okay? So the friend's trying to move after him, seeking him out, while the other one's wandering. Okay, now what would happen if we went down to add a new, suppose we wanted to have a population of size 100. All we have to do is add an experiment and say population size 100, and we could set it to be 100 people in this population. Oh, but we hard-coded it, didn't we? Yes. So go back to main, go add a parameter that's population size. Parameters are your friends, call that population size, and then make population size an int, right? Make it an int, and make it by default 100, sure. By default 2, and then I'll make it 100 for that one. And then population, we'll have a population of population size. Okay, great. Okay, so population size 100, we're going to have this size population, and now let's go look at its implications. So now we have these agents in different states. Some are friend-seeking, some are seeking out Brownian motion, and that isn't quite what we wanted either, is it? We've got a bunch of these friends who are sitting in social comfort, and then they start wandering, and a friend will often keep up and jump on them until they stop wandering. But we have this interaction of friendship and sort of wandering. So in this friend-seeking state, we just keep on moving until we're within a certain distance of this friend, and then we decay. We decay to the state where we're just in Brownian motion. So this elicits, although it seems quite close to what we had before in terms of concept, it elicited rather different behavior. Okay? So simple model shows a couple features of the movement, features of debugging, features associated with adjusting parameters. I'd like to finish this lecture, though, with a discussion of some additional types of environments, okay? So I'd like you to open a model called the game of life here, okay? How many people have seen the game of life before? Okay, a couple people. Go into help, go into example models in help, and I'd like you to scroll down here and go to game of life. It's actually, sorry, I thought it was here. So it may be called Conway's Life. The game of life. Thank you. Okay, here we are. The game of life. Thank you. Okay, great. So with the game of life, what we have is we have a, let's go to main, and let's see how this is defined. In main, if you scroll down, you will find in the space and networks area, you will find rows and columns, okay? 100 rows, 100 columns. That's separate from the width of the space in pixels, which is 500 by 500, okay? You'll notice it shows more, which is 8 neighbors. So you have north, south, east, and west, as well as northwest, northeast, southwest, southeast. Now, the rules for the game of life are quite simple, and those are associated with each cell. So if you click on cell, you will note that there's a rule for cell in this area of agent interactions. And this model will proceed in steps. First, before the step takes place, it figures out how many agents around it are alive, and then whether it is alive or dead depends on the number of neighbors around it that are alive. If the number of neighbors around it are alive are 2 or 3, and the current cell is alive, it'll stay alive. Otherwise, it dies. But if the cell is right now has nothing in it, if there's exactly 3 neighbors around it, it will start living. It'll be colonized and start living with exactly 3 around it. So, ladies and gentlemen, let's run this model. Okay, so this is showing the model evolve over time. You'll notice that cells are either blank, they're either empty, in which case they're lighter color, or they're occupied, in which case they're a darker color, a darker red. And you'll notice you can click within here to actually establish cells, okay? Or to disrupt sets of cells that already exist. What you'll see is a number of patterns here. And in fact, if you run this out, you'll see some of the patterns evolve. Sometimes that evolution is very complex. So all of this is resulting from those very simple rules that we saw just a minute ago. These rules here. So each cell determines how many neighbors around it are alive and figures out, am I going to be alive in the next time step? The resulting patterns have been very well studied. Some of them even have names associated with it. So this is called a stoplight, for example. There's patterns which are very stable. I can't remember what this is called. It goes by a certain name. There's patterns called starships, another one called a spaceship. And some of the patterns go through a variety of evolution before they settle down and kind of settle into a standard state. This is now in a repeating state. This will not evolve on its own, but if we disturbed it, for example, by clicking next to some of these items, we might be able to, for example, change its state in a way that leads to some ongoing patterns of movement. So this game of life is, in fact, computationally universal. I mentioned at the beginning of lecture that John von Neumann identified 2 major models of computation, two central models for which he's most famous. One of them is the cellular automata model, and one is the von Neumann model, so-called von Neumann model, which we have as the basis for all the computers in this room. This model of the game of life, or this game of life, is in fact computation universal. Any computation that can be performed on those computers in front of you can be performed in this game of life by setting up conditions appropriately. To put it another way, I can encode in the game of life rules for things like and, or, not. I can encode a 1 and a 0, and I can perform computations with them in this model. Now, the model to be really powerful would need a larger space, but this is a game which exhibits all the features of computational universality. In other words, it's capable of performing any computation that can be performed otherwise. This game of life is very simple in its design, but it can elicit here's a spaceship going off. It can elicit very complex behavior over time, and it is something where, it can go through many stages of evolution before settling down into a common pattern. In fact, it can go through perpetual motion by things cycling through very complicated stages. This is an agent-based model, but it is a deterministic agent-based model. There is no randomness in this. Whether a given agent lives or dies within the next time step is entirely determined by the number of agents around it. There is no randomness at all, even though we have agents at the centerpiece of this model. This is a model which has inspired a great deal of interest, both sort of academic and for hobbyists. And it's an illustration of sort of how complex patterns can result from extraordinarily simple rules. And once again, going back to the beginning of my lecture, these models, the ability to simulate this serves as a learning prosthesis. We could never think through in our heads the implication of these simple rules and all of its texture. By running the model here, we may recognize patterns, we may recognize general sort of occurrences that we would never have realized just by sitting back and thinking about it. The rules are almost as simple as you can get, but they are profound in their implications. And for those seeking to sort of enjoy a little bit, you could modify the rules. For example, you could say, well, suppose a cell lived if it had between not 2 and 3 neighbors, but 2 and 4 neighbors around it. How would that change things? And by simply running this model, you could see the patterns are actually quite different. Ladies and gentlemen, all I did was change that single line, that single bit of logic, so that a cell survives with not 2 to 3 neighbors, but 2 to 4. And look what we get. Quite different. You could modify this. You could try to add components in. You'll notice that it's kind of adjusting accordingly to sort of be self-consistent. I'm modifying it, and then sometimes I'll trigger a sizable kind of rearrangement as it tries to settle down into a new stable configuration. So again, simple rules, unclear implications without a computer to help us solve it. Unclear implications for what the consequences are unless we have a computer that will help us figure out the implications. This is 2 to 5. If they're surrounded by 2 to 5 cells around them, you could modify it. So this is 2 to 8 and run it accordingly. And for some of these, you will see very, very different patterns. Here's 2 to 8. Complex emergent behavior that is at some level surprising. We wouldn't have been able to think it through on our own implications, but it is logically implied precisely by that initial state combined with the rules. Again, no randomness here. This is no randomness. It is simply the logical consequences in deterministic rules of what's encoded there plus that initial state. So cellular automata and, in fact, these sort of discrete models are of quite some interest. And during the next lecture, I will show you a model that has considerable implications at a social level. It's called the Schelling segregation model. And I'm going to challenge you via email to try to construct it prior to class, and then we're going to be running it together. It is once again a stylized model. In contrast to this one, it has randomness, and it has to do with the emergence of patterns of segregation. But like all stylized models, it abstracts away from huge numbers of details and just keeps a few essential details. So I'm going to ask you to try to construct that at home based on a few basic principles I'll be giving you, and based on this example of the game of life. And then we'll try going over it in class next time. I'll walk through the construction of it. We'll talk through some of the implications, okay? So that's all for today. Thank you for your patience. And I look forward to seeing you next time. Please do try that home exercise before coming for class next time. And like always, I'll be holding office hours in 386 if people want to come.